Welcome to Maths with EJD. In this video, I'll continue with linear programming as we consider setting up a linear programming problem. Formulating a linear programming, linear programming. From now on, so I'll just call it LP. Formulating a linear programming problem involves defining a real-world problem in terms of objective functions, constraints, constraints, and variables. Okay. So I'm here to give you a step-by-step guide, a step-by-step guide on how to translate a word problem into an LP model, into a linear programming model, followed by detailed examples. So I'll give you examples, followed by detailed examples in both business and manufacturing. Okay, so let's go with the steps first. Steps to formulate an LP problem. So the first step is to define the decision variables. We already talked about this terminology in the previous video, so you can refer to that. Define the decision variables. Okay, so here you have to identify the quantities, identify the quantities you want to determine. These are typically unknowns in the problem. Then number two, you have to formulate the objective function. Formulate the objective function. So here you determine what you want to optimize, to optimize. Usually maximizing profit, usually maximizing profit or minimizing costs. In the general sense, right? It's more like you want to minimize what you don't like and you want to maximize what you like, something like that. So, I mean, as a manufacturer, for instance, you want to keep your cost as low as possible and keep so that you can have a wide profit margin as possible, as much as possible. So then you can now express this objective as a linear function of your decision variables. So after doing that, the next thing is to set up constraints. Three, set up constraints. And with this, we mean identify restrictions, identify any restrictions or limitations in the problem, like resource limits, budget constraints, or production capacity. You can have all the raw materials you need, but you may not have the capacity to, produce as much as you would like to. So you formulate each constraint, formulate, let me tell you that's a part, formulate each constraint as a linear inequality or equation. Okay, then number four, you have to include, include non-negativity constraints. Of course, that is, in most cases, it is necessary, except if you have unrestricted variables. Include non-negativity constraints. That is to guarantee positivity, right? For instance, in business, right, you don't want to expect to have negative profit or negative production or anything like that. So you have to include non-negativity constraints. So most, not all, right? Most LP problems require decision variables to be non-negative, since negative values might not make practical sense. E.g., negative production, or negative money. Okay. Now that takes us to some examples. Let's see the first example. Example one. Here it's about business, and we are maximizing profit from advertising. Maximizing profit from advertising. Okay. Um, Look at the problem statement. So a company has $20,000 to spend on advertising in two magazines. I mean, that already looks like a constraint, right? It means the company cannot spend more than $20,000. So that's already a limitation. Company has $20,000 to spend on advertising in two magazines. A in two magazines. Okay. That's magazine A and magazine B. Each advertisement, each advertisement in magazine A costs $2,000. And each advertisement in magazine B costs $3,000. Okay. Again, each ad in magazine A reaches each ad in magazine A reaches 50,000 people, and each in magazine B reaches 60,000 people. The company wants to the company wants to reach at least uh at least 180,000 people. How should it allocate? How should it allocate its advertising? How should it allocate its advertising budget to maximize exposure? So that's the question to deal with. Right. And we can go about it this way. We can have step one. Step one, define the decision variables. From what you've seen already, define decision variables. So you can say let X be number of advertisements in magazine A. Okay. And then Y now is number of advertisements, number of advertisements in magazine B. Okay. Once that is defined, we can talk about step two. Step two. Like we saw before, you can formulate the objective function now that you know the meaning of not the number of advertisement. Formulate the objective function. Formulate the objective function. And how do you do that? Now, we know already that the company aims to maximize the number of people reached, the number of people reached. That's the objective of the company. Not to maximize the number of people reached. So in that case, the objective function will be to maximize Z, which is equal to, X is the number of advertisements in magazine A, which can reach 50,000 people. Okay. Then Y is the number of advertisements in magazine B, and each ad can reach 60,000 people. So it means the total number of people that can be reached with X number of advertisements in A is 50 times X, while the total number that can be reached by B is 60,000 times Y. So in this case now, we want to maximize Z equals 50,000 X plus 60,000 Y. Okay. So that's our objective function in that case. Then we go to step three, where we set up constraints. Step three, So in step three now, you have to set up constraints. Okay. So, and from the question right there, we have seen different kinds of constraints. The first would be the budget constraint. Okay. You can only spend so much. Uh, budget constraint. So here now, the total spending cannot exceed $20,000. Okay. And you already got that. Each so each advertisement, one advert, or let's say one ad in Mag A, if I can put it that way, one ad in Mag A costs $2,000, and then one ad in Mag B costs $3,000. Okay. So in that case, total spending can now be the total this the number of adverts you can have in A is X, and that's which you can have in Y in B is Y. So you have X here and you have Y here. So it means that whatever you're doing, 2,000 times X plus 3,000 times Y can only be less than or equal to 20,000. So you cannot spend beyond 20,000. So you can spend less than 20,000 or minimum or 20,000 at most. So that's why you can spend at most $20,000. That means less than or equal to 20,000. So that is our first constraint. Then um we go again for step four. Okay, that's one constraint, right? Is about the another constraint another constraint, which is constraint two. We saw there's a reach constraint, right? We want to reach at least 180,000 people, 180,000 people. So we have a reach constraint. Okay, a reach constraint. So the ads should reach, the ads should reach at least, at least 180,000 people. 180,000 people. So that means we have okay, one ad in Mag A can reach 50,000 people, like we saw before. Then one ad in Mag B, in Mag B reaches 60,000 people. So again, if you put X, so in A you have X and Y, and B you have B. So it means that 50,000 X plus 60,000 Y should be greater than or equal to 180,000. Talking about reach now. So that's your second constraint. Then after all this now, you have the okay, before I even talk about this now you see it's important to pay attention to this idea. Um if you have at most, at most is less than or equal to, then at least is greater than or equal to. So when you come across that, but if it is specific, that would just be equal to. So if I say you can spend 20,000, you should spend 20,000 exactly. So in that case, that would be equal to. So at most less than or equal to, at least greater than or equal to. So we have the reach constraint taken care of. Then we have the third constraint, which is almost always there, except if the variables can be negative. So we have the non-negativity constraint. So whether you're told or not, this is important. So you have the non-negativity constraints. So in that case, now it means the number of adverts that can be placed in A, which is X, cannot be great, cannot be negative. So it's either you don't patronize magazine A at all, or I mean that's all. I mean it's either you patronize them or you don't patronize them. So if you don't patronize them, that is zero adverts. It can't go negative. Same for the magazine B. So you can have zero adverts or greater than zero adverts with them. So those are the constraints now. So with all of that now, we can now we can put everything together. So maybe I can call that step four. Step four. Step four. So in step four now, we can have a kind of overall problem formulation. So here you just put everything together. So, and that is simply this: maximize z equals 50,000 x plus 60,000 y. Okay. Then the constraints will be presented like subject to the first constraint is 2000 x plus 3000 y less than or equal to 20,000. And then the second constraint is 50,000 x plus 60,000 y is greater than or equal to 180,000. And you have the non-negativity constraints that and y are both greater than or equal to 0. So, I mean, that's the formulation of the problem. This video is all about formulation, but we just want to learn about how to set up a linear programming problem. So from the next video, you'll be seeing how different approaches for solving these kind of problems. Okay, so we have successfully formulated our problem and it's so clear. Well, I always like to do a kind of fast way of interpreting the question. So if you are in an exam situation, I just need to interpret this to make things very clear from the get-go. So you can start writing immediately. So I'll do that kind of rushing. I mean that kind of sharp, that fast way of getting things done. So a company has $20,000 to spend on advertising in two magazines. So you can already see straight uh how do I say it? Let me say smart approach. Smart approach that as you're reading the question, you're writing it down straight so that you can see how it looks like. So a company has $20,000. That's just like budget is less than or equal to $20,000, something like this. Then next, uh, in two magazines. So straight, you have magazine A and magazine B. You can just indicate that straight up. And then um magazine A, magazine B, straight. Then the next thing is this that an advert in magazine A costs $2,000. So you say add costs if you like, add advert cost now. So in magazine A it's $2,000. Magazine B it's $3,000 straight. Then each ad in magazine A reaches 50,000 people. So you can say add reach. So each one in A reaches 50,000 people, 50,000 people, and each one in B reaches 60,000, not money now, 60,000 people. Now it's people. Okay. Then what else do we have? The company wants to reach at least 180,000 people. So we want reach to be greater than or equal to 180,000. So, I mean, by just reading through the question and writing this down, you already have a very clear idea of what needs to be done. So the company wants to reach at least 180,000 people. How should it allocate its advertising budget to maximize exposure? So the question is, how should it allocate its budget? So it's about budget allocation, right? So, and we know already that, so once you have written this down, the next thing you just want to do is you can quickly just say, okay, X is number, some sharp, smart way. maybe this can be on a rough paper so that by the time you're writing, you're not just writing this, or you can just write this by at some side, which is not for grading, so that by the time you're presenting your work, it's neater. So X is simply not number of ads in A, number of ads in A. Then Y is number of ads in B. So once you establish that, then you can just come here and say, okay, for A, ad cost is 2,000. So you can just say this is X, this is Y straight, and of course, and we don't want, we cannot, no matter how we spend, it has to be less than or equal to $20,000. Okay. So you have one constraint already taken care of straight up. Then ad reach, it can reach 50,000. A can reach 50,000, so multiply by X, multiply by Y. And in total, we want to have greater than or equal to 180,000 reach. Okay, but there's something we have not done, which I probably should have done first, and that is the objective function. Here, we want to maximize the number of people reached, right? What we want to maximize is the number of people reached. So since it is about reach, you still have to focus on this, right? So it means your objective function is still going to come from here. So we know that should be like, so our Z in short will just be 50,000 plus 50,000 X, 50,000 X plus 60,000 Y. That is your objective function. So you can now write out the whole problem that, okay, you want to maximize Z equals 50,000 X plus 60,000, 50,000 X, 50,000 X plus 60,000 Y, then subject to the constraints you have outlined already. That's 2,000 X, so 2,000 X plus 3,000 Y is less than or equal to 20,000. And then you have 50,000 X plus 60,000 Y is greater than or equal to 180,000. And then you have the X and Y, which have to be non-negative. So with that, I mean, that's a very smart way. And I'm going to use that approach for the second problem. So instead of having to go through all the steps, so that, because time can be of essence too. Because, I mean, here we are not even solving. You are just interpreting. But if you have to solve, that will take a bit more time. So let's go for a second example. So let's say um, example 2. So for example 2, we are considering manufacturing, and that is minimizing production costs. Minimizing production costs. Okay, that's what we're doing here. And this is a problem statement. Problem statement. So imagine that a factory produces two types of products. That's products X and Y, products X and product Y. Okay. Um, each unit of product, each unit of product X requires 3 hours on machine A and 2 hours on machine B. Machine B. Okay. Again, each unit of product now, each unit of product, each unit of product Y requires 4 hours, 4 hours on okay, first each unit of product X requires 3 hours on machine A and 2 hours on machine B. Okay. Oh, that's each unit of product X. Now, each unit of product Y requires 4 hours on machine A and 1 hour on machine B. Okay. Again, machine A has 120 hours available. That's a constraint. 120 hours available. So no matter how hard you try, you can't use it for more than 120 hours. And machine B has 70 hours available. Okay. Now, profit, if the profit per unit of production, if the profit per unit of production, if the unit profit per unit of product X is $30 and per unit of product Y is $40. Okay. So the question is how many units of each product should the factory produce to maximize profit? Okay. So that's the question. Now, like I said, I'm going to use that past method. So let's talk about formulation now. So to formulate using the fast method, like I said, you just read through and you start writing things down. So a factory produces two products, X and Y. So here we have product X. So we say product, this is X, this is Y. Okay, straight. Then the next thing is product X and product Y. Each unit of product X requires 3 hours on machine A. So say for machine A now, so we know there's a machine A and there's a machine B. Okay, so um each unit of product X requires 3 hours of machine A and 2 hours on machine B. Then each unit of product Y requires 4 hours on machine A and 1 hour on machine B. Okay, so it's coming out gradually, as we can see. So what other information do we have? Machine A has 120 hours available. Okay, so here now, machine A only has total of 120 hours available. Okay, machine B has a total of 70 hours available. So those are constraints, obvious constraints. Then, okay, apart from that now, what else? We have profits, right? If the profit per unit of product X is $30, so we say profit per unit of product X is $30, then product per unit of product Y is $40. So the question is, how many units of each product should the factory produce to maximize profit? So how do we know the variables to use here? So we are talking about units of each product, units of each product. So straight up, uh we can just say let X be the okay, that's like a twist, right? So it's better to change. Let X be the number of number of products X produced. Okay. And then sure, Y, we now let Y be the number, of products Y produced. So once that is settled, right, you can then go back. So you already know this is going to be, so for the machine A time now, so you have 3x, 4y. For machine B, you have 2x, 1y. of course, and that will be less than or equal to 120 hours and less than or equal to 70 hours respectively. And of course, here, so it is profit we want to maximize like that. So of course, when you as you maximize profit, you are minimizing cost for sure. So here you have 30x 40y like that. So in that case, now you can now show the overall problem formulation, overall problem formulation. Again, we are maximizing profits. That's what the objective is. That's how many units of each product should the factory produce to maximize profit. So again, it's a maximization thing. So now we have maximize z equals 30x plus 40y. The 30 times X. So 1 unit of X gives $30. So that's 30 times X in profit. Then the other one is 40. So 40Y in profit. And then that will be subject to the first constraint is about machine time, time on machine A. So that will be 3X plus 4Y, 3X plus 4Y less than or equal to the available 120 hours on machine A. That's constraint for machine A. The second constraint is for machine B. That is 2x plus y is less than or equal to 70. 2x 2x plus y is less than or equal to 70 hours. And the third constraint, which we can always take for granted, is the fact that the of course in a production process you cannot have negative production. So x and y have to be greater than or equal to 0. And with that, we formulated that problem. So it's pretty easy. So you can just use that smart approach. So there are, I mean, all manners of problems we can also see, like marketing allocation, production planning, resource allocation, and all the rest. So with this, we come to the end of this video. It's such an interesting thing, and it's very useful in every aspect. This is not looking quite like greater than, so let me rewrite. So if you have not subscribed to this channel, you want to definitely do that. Then very importantly, you want to hit the notification bell so that each time a new video is released, you can get alerted. And don't forget to comment, tell me if you wanted to teach a topic or solve a problem. Then also like and share so that more people can have access to this great learning. Till I come your way again, keep optimizing. Bye.